Hello, my name is Jamshidbek Mirzakalov, and I'm a master's student at the University of South Florida. Today I'll be presenting our group's work on the topic of towards a task-agnostic model of difficulty estimation for supervised learning tasks. Previous work has shown that organizing the training set in a meaningful order can have a significant impact on downstream performance and reduce training time. And the way we achieve this meaningful order is called like a curriculum. And the training strategies that use a curriculum called curriculum learning. Since Joshua Benjo's seminal work in 2009 in curriculum learning, many training paradigms have emerged, namely some for NLP as well. And many curriculum learning training strategies for NLP can be categorized into two groups. The ones that use a handcrafted feature or a set of features to measure difficulty, and that's designed for the task that they're working with. And another group of approaches, the ones that use a separate model to predict the difficulty, whether it be a meta-learning approach or a completely offline trained model to predict the difficulty. In this work, we investigate how we can measure the difficulty of a sample in a more task-agnostic way by using human participants. Intuitively, this allows us to gauge a difficulty signals from human participants, which we argue in principle can be applied to any supervised learning task. In this paper, we focus on natural language inference tasks, namely SNLI, because unlike many NLI tasks, SNLI def set includes five predicted labels from each participant during the data collection phase. For our experiments, the objective function we use is our models try to predict how many of the participants out of the five will get the given question right. Intuitively, this gives us a measure to difficulty regardless of the task, and as well as um, if more people get the question right, the easier the question it is, and that's the intuition that we go by. And to test this, we experiment with a variety of linear, non-linear, neural, and non-neural models for both regression and classification type of tasks. The features we experiment with different feature sets as well. In this case, for the premise and hypothesis, we calculate the sentence embeddings using the sentence transformers library taken from Roberta. And you can see on the screen that we, as the features, we use cosine similarities, sentence length, flattened embeddings, which is basically the sum of two embeddings of the premises and hypothesis. Concatenated means that we put them back to back and we feed them into our models. So in terms of the regression results, top four results are here actually from the non-neural models. The best performing model so far was a decision tree, which gives a mean of 84, and the score 0.84 Spearman's correlation. And this results on the dev set, and then we perform tensor cross validation, and um, they perform about the same mean score for across all folds. Interestingly, two neural models. The first the fine-tuning of a pre-trained Roberta language model, and the training of a neural network from scratch named DNN performed really badly in this case, achieving a very weak correlation in terms of Spearman. And we suspect that this is due to the fact that they are overfit to the training set and they cannot generalize onto the test set because how little the data is in this case. For the classification task, uh, we structured the problem as the model will try to guess how many people will get the question right. And in this case, decision tree again performs the best, achieving 0.83 in Spearman's correlation. However, support vector classification does not achieve as high of a correlation anymore. When we look at the analysis of her regression models, on the left you can see the difficulty assignments using our best linear regression model, which achieves a weak correlation, and on the right you can see our difficulty assignments using the best regression model, which is the decision tree. And this is when we use the model to project the difficulty estimations onto the training set, which has almost 500,000 samples. If you look at the distributions, they look almost exactly identical. However, when we do a more deeper analysis, we find that about 16% of all questions are given opposite predictions, and that the mean difference between the difficulty scores of these two models is 0.41, which shows that even though the trends may look very similar, the kind of difficulty assignments that the models are making are fundamentally very different. And when we look at the classification models, again, on the right, you can see the best classification model, which is our decision tree model, and on the left, you can actually see the difficulty assignments gathered from human annotations from the training set. Uh, and here also it follows about the same trend. Since most of the human annotators got the questions right, you can see that the data is skewed towards this one, which is that everyone got the question correctly. In conclusion, in this work, we propose a method for creating difficulty models using human annotations, and we argue that this principle can be applied to any supervised learning task. And some future directions for our work is we want to experiment with more data sets such as MNLI or even tasks beyond NLI, where we can actually collect human responses and create these models of difficulty and analyze them. Also test their impact on the performance of the model. We also want to see how if we can use the curriculum learning for to um, improve the performance of language models, and we can use fine tuning during the fine tuning, and we can study its efficiency. We can study the effect of different sampling protocols. Instead of references, thank you for your time.